The electromagnetic spectrum is one of the most fascinating topics in introductory chemistry. And even though it might feel like it belongs in a physics course, the electromagnetic spectrum and its fundamentals explain how light can interact with matter to give rise to ionization, to the colors that we see, and why particular forms of matter absorb light at different wavelengths. And so in order to get to those ideas, we first need to build some fundamentals by understanding how we characterize light. So what we're going to start with in this video is just taking a look at a light wave and talk about the different ways that we can characterize it. In particular, we're going to talk about wavelength, frequency, the speed of light, and energy. So let's start at speed of light, because speed of light is absolutely going to be constant. And this is going to represent the speed of light in a vacuum. It's going to be unchanged, and no matter what the wavelength, frequency, or energy of a light wave is, it's always going to have a particular speed equal to 3 times 10 to the 8th meters per second. Next, we're going to talk about wavelength, and wavelength characterizes the distance between trough to trough or peak to peak in that wave, and that's going to be just exactly what you see here, typically measured in a distance, or let's just call it meters. Next, we're going to have what we call frequency, and frequency is a little bit more difficult to understand, and so let's actually set up a little experiment to demonstrate what frequency is. So if I put a sensor right here and I wanted to know how many wavelengths pass this particular point in a certain amount of time, let's just call it 1 second, that would actually be the direct definition of frequency. So let me write that out, where frequency is going to be equal to the number of wavelengths to pass a point per second. Now notice what I wrote here. I wrote a very fancy V. That is the Greek letter nu, which we use to represent frequency. And the units of this are actually going to be all based on this per second. And so the units are going to be a hertz, which is equal to an inverse second, or 1/second, or a per second. So in order to kind of fully characterize this, I want to actually draw another light wave that's going to pass this same point. So I'm going to draw a red light wave, of course not drawn to scale, not very pretty. But what you'll see as the difference here is that this red light ray is going to have a longer wavelength. And so in a given amount of time, because these have to be both traveling at the same speed of light, the red light is going to have fewer wavelengths past this particular point. And so the red light is going to have a lower frequency. Now, if we bring these concepts into a single mathematical equation, it looks like this. The speed of light, c, is equal to the wavelength times the frequency. If we look at the units here, what you'll see is that this is meters per second is equal to meters times inverse seconds, and so it works perfectly. But just like in that example that we saw, we want to talk about the conceptual relationships that exist here. The speed of light is going to be constant, but as the wavelength went up, the frequency went down. And so the opposite would be true as well. If the wavelength goes down, the frequency is going to go up. Now this is the definition of an inverse relationship. And that is what exists between the wavelength and the frequency. But there's one more term I want to bring in here, and that's going to be the energy. And I really just want to show you the formula here. So energy is going to be equal to what we call H, or the Planck's constant, times the frequency. And so energy is going to be measured in what we would call a joule. The Planck's constant is a value, like the speed of light, is set in stone, and that's going to be equal to 6.626 times 10 to the negative 34 joule times seconds. And that is one of the tiniest numbers that you will ever use in chemistry. But you see that its units fulfill a purpose, because when I put frequency in here, the frequency is going to be inverse seconds. And so the role of this constant is to cancel out these units and get you just to energy. So pretty cool there. Lastly, before we get into a couple of questions, I want to talk about why this is so important. If we look at this diagram at the bottom left, what you see is a series of hopefully pretty familiar wavelengths of light. You've got radio waves, microwaves, infrared. You have the rainbow, so all the visible light. And then you have UV, X-ray, and gamma rays. And what's important to see here is that as you go from left to right on this diagram, you're increasing in energy, you're increasing in frequency, but you're shortening the wavelength. And so you see that inverse relationship there between energy and frequency and wavelength. As energy and frequency go up, wavelength goes down or shortens. Now, if we zoom in and just kind of focus on the visible spectrum here, there is a mnemonic device I recommend knowing, which is ROYGB. I'm kind of fading away here, so BIV. Roy G. Biv. It's something that you should definitely know, and that basically what it's doing is it's listing the distinct colors of the rainbow in order of increasing energy. So red is the lowest energy on the visible spectrum with the longest wavelength, and violet would be the highest energy with the shortest wavelength. And that's important to note because this is the point where electrons in matter actually begin to get excited. And what that means is you can actually boost their energy, but they remain intact on the atom or molecule. But when you get to even higher energy levels, we talk about UV being dangerous, UV from the sun, or X-rays. You have to wear those protective vests if you get an X-ray, or gamma rays, which hopefully you don't have much experience or exposure to. But all of these, as energy continues to get higher and higher, suddenly you get to the point of what we call ionization. And ionization is when the electron can be fully withdrawn or emitted from an atom or molecule. And that can break bonds, that can lead to complications in the human body. And so it's really important to be able to characterize that energy of the high energy light waves. So the next focus of this video is going to be on a couple of questions. And so let's transition over to those questions and see if we can implement these concepts in both calculation and conceptual questions. All right, so here we see two questions. One is going to be a conceptual question and one is going to be an actual calculation, which we'll work through in a couple different ways. But let's start with number one and see if we can implement those concepts that we just discussed. So number one is, compared to a yellow light wave, a violet light has a blank wavelength, a blank frequency, and a blank energy. And what we're looking for is something like longer, shorter, greater, smaller, something like that for each of these blanks. And so what we're talking about is the relationship between wavelength, frequency, and energy. And so let's start with the colors that we're discussing here. And these are definitely in the visible spectrum, which is that Roy G. Biv that I was talking about. So as we go from left to right here, this is going to be the higher energy, higher frequency, but then it's going to be the shorter wavelength. And if you want to put all this together, remember that as energy goes up, frequency goes up, but wavelength is going to go down. And it would be the opposite if it were energy going down, frequency going down, wavelength getting longer. And so let's see if we can use this information to fill in these blanks. Compared to a yellow light wave, which you would find right here, a violet light ray, which you would find right here, has got to have a shorter wavelength, let's call it a greater frequency, and a higher energy. And you could use maybe different words here and there, but that is probably the best way of describing each of these. So now let's see if we can make an actual calculation here. And so this is asking, what is the energy of a 108 nanometer photon? Now, a photon is just let's just say a light wave, because I don't want to get too much into the quantum mechanics of, is it a particle, is it a wave just yet. So when I see energy, I'm definitely thinking of this formula right here. E is equal to h nu, where h is the Planck constant and nu is frequency. But I'm starting off with a wavelength, and so I'm going to bring this equation into the picture as well, because I need to have a way to get to frequency from wavelength. I also see something that's very important here, which is that we're dealing with a 108 nanometer photon. So what in the world is a nanometer? This is something that you'll get very familiar with in this particular unit, because we're dealing with such tiny wavelengths here. So 1 nanometer is going to be equal to 10 to the negative 9 meters. That is a tiny, 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 tiny distance. But let me show you how I make sense of this if I'm using this in a particular calculation in a question. I replace that prefix. As long as I know what it represents, I'm going to replace that prefix with what it represents. So I'm going to replace that n with a 10 to the negative 9. So this becomes 108 times 10 to the negative 9 meters. And so when I use this in a calculation, which I have to be in meters if I'm dealing with speed of light and frequency and energy, this is the value that I'm going to use. So let's get into the actual calculation. So the first thing I want to do is get the frequency. And the way I'm going to do that is use this formula right here. I'm going to say that C is equal to lambda nu. I have C because it's a constant. It's 3 times 10 to the 8. And then I have the wavelength because it was provided in the question. So C over lambda is equal to my frequency. That's going to be equal to 3 times 10 to the 8 meters per second divided by 108 times 10 to the negative 9 meters. And this actually gets me to an answer of about 2.7, and this is going to repeat, times 10 to the 15 inverse seconds, or hertz. Now I can solve for energy. And this is going to be my E is equal to h nu, which is just equal to my constant, 6.626 times 10 to the negative 34 joule times seconds. And I'm going to take that value multiplied by my frequency, inverse seconds, to get me the actual answer. These seconds are going to cancel out. I'm going to end up with just joules, and it's going to be about 1.84 times 10 to the negative 18 joules. But let me show you a little bit more succinct of a way to do this. If you're looking at these, and you said that all I did in step 1 is I solved for the frequency using this relationship right here. So why not just plug this into the energy formula so that I don't need to break this up into 2 steps? And what that would look like is I'm saying E is equal to h nu, but I said that nu is equal to C over lambda, or wavelength. So I can just use E is equal to h times C over lambda. And I can write that a little bit neater, where I say that E is equal to hc over lambda. Now, see if you can plug this in, and what you'll notice is that in one step, you will get to this exact same answer.